This schema represents the backbone of an ISP, with the core routers in the green area in the center, and some border routers in the blue areas on the left and the right. Let's focus on one of the border sites. 6Winds vRouter will run on the border routers. They are usually redundant. The border routers are connected to border routers of other ISPs. And these ISPs themselves are connected to other ISPs, forming the Internet. eBGP is used with the transit routers to exchange external routing information, and iBGP and OSPF are used with the core network to propagate the routes. We will use an Ixia traffic generator to simulate the Internet traffic at 20 gigabit per second. Let's start by reviewing the IP configuration of the different interfaces. A lag interface is used towards the PE routers in the core to provide active standby high availability with the redundant border router. The traffic towards each of the transit routers is encapsulated in VLANs, and we use a loopback interface for iBGP. Let's review the BGP configuration. Here we see the iBGP pairings with the PE routers, as well as the eBGP pairings with the transit routers. And also the iBGP pairings with the other border router for high availability, and the intelligent routing platform for routing optimization through BGP Flowspec. OSPF is used internally to learn the IP addresses used for iBGP with the PE routers and the other border router. Let's now review the BGP state. In the BGP summary view, we see the BGP full routes learned from the transit routers and from the other border router. There are 4 full routes configured in the system and 1.3 million RIB entries. Commands are available to review the routes advertised to a specific router, here to the transit router towards ISP1, and conversely, we can see the route received from this same router. There are a lot of them as we receive the BGP full route from this router. Let's now review the monitoring and analytics mechanisms used in this demo. The vRouter is connected to the ISP's EMS. We can review the configuration of the KPIs that are retrieved from the system and sent to the time series database of the EMS. These include product information such as license and version, system information such as CPU or memory usage, networking statistics, and others. These KPIs are periodically exported to an InfluxDB time series database and will be displayed in the Grafana dashboard as we will see in a few seconds. And for the data plane statistics, sFlow is used to export data plane samples to the EMS. This information will be used to chart how the traffic towards diverse destinations is dispatched among the different transit routers. We can dump traffic on the core network to see the sFlow v5 packets toward the EMS. Now, let's simulate some traffic towards Netflix, YouTube, and the rest of the Internet. We use an Ixia traffic generator for that, and we generate 20 gigabit per second of traffic. In the Grafana dashboard on the EMS, we can see how the KPIs are displayed for continuous monitoring of the system. We see system uptime, vRouter status, memory and CPU usage, network interfaces with their throughputs, process and users information, disk usage, and IPv4 neighbors and routes configured in the system. We can see that 700,000 routes are installed in the FIB. Regarding network traffic analysis, the AES stats dashboard is filled in thanks to the sFlow information. We see 3 graphs according to the destination of the traffic, and the colors indicate the transit router used to reach the destination. We can see that YouTube is reached through transit 1 in pink, Netflix through transit 2 in light blue, and the rest of the Internet through transit 3 in dark blue. It's now time to optimize network traffic. As we have seen, Traffic to YouTube goes through ISP1, traffic to Netflix through ISP2, and traffic to the rest of the internet through ISP3, according to BGP and AS path selection. At some point, the IRP detects that it is more optimal to reach the internet through ISP1 compared to the path that was originally selected by BGP. BGP Flowspec is used to alter the RIB into the vRouter using policy-based routing. As a result, the traffic towards the internet starts flowing through ISP1. Let's now review the BGP Flowspec functionality that allows for network optimization. We can see the state on the vRouter on the left when no Flowspec information has been received yet. On the IRP, we will use the ExaBGP tool to send the Flowspec rule to the vRouter, asking to redirect the flow with destination 888.0/24 that simulates the internet traffic through transit router 1. We can see on the vRouter that a BGP Flowspec prefix has been learned. And this translates into an ACL and a policy-based routing rule that will take precedence over the routing path that was computed by BGP. To conclude, let's check the AS stats dashboard. We can see that the traffic towards the rest of the internet now goes through transit 1, as the pink color in the first graph indicates.